Data analysis is a set of processes for gathering, inspecting, organizing, and displaying data with the goal of discovering useful information that will either add, support, or diminish support for a hypothesis. The requirements for proper data collection must be clear and unambiguous. Understanding where data comes from and how it is collected is of paramount importance. Measures of central tendency. The mean of a data set is the sum of the numeric data values divided by the number of data values. It is often called the average. The equation is given on the AP Biology reference sheet as the sum of all numbers divided by the total number of data values. The median of a data set is the middle data value when the values are written in numerical order, typically from smallest to largest. The mode of a data set is the data value or range of data values that occurs most often. Example 1, mean, median, and mode. Find the mean, median, and mode of the ages for data given below. If I'm given a set of 5 ages, 10, 8, 9, 8, 5, find the mean by adding the values and dividing by the number of values. Find the median by listing the values in numerical order and selecting the middle value. And find the mode by selecting the value or values that repeats most often. Okay, so to find the mean, we add up each of the individual values, 10, 8, 9, 8, and 5. We get 40. And divide by the total number of values. So there's 1, 2, 3, 4, 5 values. Gives us a mean of 8. If I list the numbers in order from smallest to largest, I can find the median or the middle value is 8. And the mode is the value that repeats the most often. In this case, 8 is the only value that repeats. In this case, the three measures are equal: mean, median, and mode. That is not generally true, but is true if the data represents a normal distribution. Some special cases to be aware of. For the mean, calculating the mean or average of values won't always result in a whole number. To calculate the median when there are an even number of values, so there is no midpoint, average the two middle numbers. So add those two together and divide by 2. And for the mode, it is possible to have more than one mode if more than one value is as repetitive. Also, it's possible to have no mode if no values repeat. Example 2, calculate the mean, median, and mode for these data. So the set of numbers 1, 3, 4, 4, 5, 5, 8, 11. Conveniently, they're in order from smallest to largest value. Let's find the mean, median, and mode. Okay, so to find the mean, we have to add up each of the values. 1 plus 3 plus 4 plus 4 plus 5 plus 5 plus 8 plus 11. We get 41. We divide by the total numbers in this set, which is 1, 2, 3, 4, 5, 6, 7, 8. So divide by 8. Get 5.125. Notice this is not a whole number. The median in this case, we have 8 values. So there is no exact midpoint. It would be in between these two values here, right? And so with an even number of values, the median is the average of the central values. So I add this 4 plus 5 and divide by 2 to get a median of 4.5. And for the mode, in this case, it's possible to have more than one. We have 2, both 4 and 5. Example 3, calculate the mode for these data. 1, 3, 4, 5, 8, 11. There is no mode in this case since no value appears more frequently than any other value. Example 4, find the mean, median, and mode of the ages for the Apollo pilots given below. So for Apollo missions 11 through 17, We have the pilot's age, 39, 37, 36, 40, 41, 36, 37. And we need to find the mean, median, and mode of this set of ages. So the mean, we just add each of the ages up. So 39, 37, 36, 40, 41, 36, 37, just add all of those. We get 266. Divide by the total number of pilots. So 1, 2, 3, 4, 5, 6, 7. And we get a median of 38 years. A mean of 38 years. The median, in order to find the median, we need to put these ages in order. So this is random right now because it's in the order of the Apollo missions. But if I put the set in order from the youngest to the oldest, I can find the midpoint of the data set. So the median is 37 years. The modes, there are two because both 36 and 37 years appear twice. Extreme values and range. The minimum is the smallest value in a set of data. The maximum is the largest value in a set of data. Together, the minimum and maximum are called the extreme values. The range is the difference between the maximum value and the minimum value and is always a non-negative number. Example, minimum, maximum, and range. For this data set, 14, 17, 9, 2, 4, 10, 5, what is the minimum? What is the maximum? What is the range? So we can see from the data set the minimum value is 2, the maximum value is 17, and the range would be 17 minus 2, or 15. Types of graphs. These are the 6 types of graphs which you will need to be able to create or interpret. You need to be able to determine the best graph to use based on the type of data. Scatter plots and line graphs are used when the value of each variable depends on the value of the other, and each variable can be considered as continuous over a range of values. Bar graphs and pie graphs are used to represent discrete data. The variables are not continuous, nor do they necessarily span a wide range of values. Histograms and box and whisker plots show the distribution of continuous values of a single variable for data, which may or may not be normal, i.e. parametric. Parametric data will be discussed later. Scatter plots and line graphs. This set of data shows that for each value of one variable, there is a corresponding value of the other. For every math grade, there is a science grade. It implies that the variables are defined over a wide continuous range. Whether there is a pattern relating the variables to one another is best determined by first graphing the points. In the graph, we've plotted the math grade on the x-axis, the science grade on the y-axis. This shows that there is a mathematical relationship between the points, so a scatter plot is a good choice. In this case, the relationship is linear. The next step is to draw a line of best fit, which is drawn so as to pass nearest the highest number of points. It need not pass through any of the points. The line provides the relationship between the variables and implies that it is the same between and beyond the measured values. Whether that is true would need to be confirmed by further experiments. Once the line is found, the relationship between the variables is fully described by the line's slope and intercepts. If a line of best fit can be drawn, it reveals the correlation between the two variables. This line has a positive slope, so it reveals a positive correlation between the variables on the two axes. As one of those variables increases, so does the other. This line has a negative slope, so it reveals a negative correlation between the variables on the two axes. As one of those variables increases, the other decreases. In this case, a line of best fit cannot reasonably be drawn. This reveals that there is no correlation between the variables on the two axes. A change in one of the variable will not result in a predictable change in the other. Now, let's do an analysis of an alternative set of data. Plotting the points for this set of data leads to a different conclusion about the best graph. These points reveal more detail than can be captured by a single line of best fit. Instead, a line graph will be used. In a line graph, all the points are connected by lines. This graph implies the relationship between the values between points on the line connecting them, but not beyond the range of the points. Conclusions can be drawn from this graph, but the relationship between the variables is more complex than could be captured by a line of best fit. Pie graphs and bar graphs. Both bar graphs and pie graphs can be used to represent discrete data. Here, the same data is represented with either type of graph. So this is U.S. energy consumption per sector in the year 2007 from the U.S. Energy Information Administration. And you can see as a percentage of U.S. energy use, 4 different types of energy: transportation, industrial, electric power, and residential. So you can see on the bar graph that discrete data, or on the pie graph as a percentage of the pie. A pie graph is a circular statistical graphic which is divided into sectors to represent numerical proportion. The arc length or area of each sector is proportional to the quantity it represents. While it is named for its resemblance to a pie which has been sliced, there are variations on the way it can be represented. So on the left, you see the same pie graph from the previous slide. And on the right, you can see a different representation of a pie graph where the quote-unquote slices, as they are not connected in the same way. The data in this table is discrete in that the names of the labels do not represent continuous values that span a wide range. So the names of the labels: water, acetone, methyl alcohol, and ethyl alcohol. The bars of the bar graph or the slices of the pie graph could be listed or graphed in any order. Whereas with line graphs and scatter plots, the order of the points along either axis is determined by their value. The bar graph is a great way to represent data from experiments in which the independent variable is discrete, not continuous. No relationship is implied by the order of placement of the substances along the x-axis. This means that the independent variable is discrete, not continuous. Histograms. While histograms look a lot like bar graphs, they are very different. Histograms represent the distribution and frequencies of the values of a single continuous variable. It is used as part of a statistical analysis when the data set is too large to be displayed by a scatter plot or line graph. Categories are created for the data, and each data point is assigned to a category. The height of the bar of the histogram for that category represents the frequency of that value. Since the data on the x-axis is continuous, its order is not arbitrary, and there are no spaces between the bars, as there is in a bar graph. So, let's say, for example, that we were given 1,923 students that were to receive grades which range continuously from 0 to 100. We can divide those up by intervals, such as A equaling 90 to 100, B equaling 80 to 89.9, C 70 to 79.9, D 60 to 69.9, and F 0 to 59.9. The number of students who received each of the 5 possible grades is shown in the table. The number of A's, B's, C's, D's, and F's. And this should total the 1,923 students. These data can then be shown in a histogram. Unlike in a bar graph, the values along the x-axis have a prescribed order, A, B, C, D, F in this case. The opposite order from F to A could have been chosen, but A could not have been placed between B and C because we're talking about a continuous increase from 0 to 100. Also, the bars are adjacent since they include all possible values. In bar graphs, the bars are spaced apart since they are discrete. This captures the grades of 1,923 students in a simple-to-read format. Compare and contrast bar graphs and histograms. Data in different categories can be displayed using bars with lengths that represent frequency. Histograms show data in intervals along a continuum. Bar graphs show a specific value for a specific category and have a space between bars to separate the categories. So you can see in the histogram here, we have age on the bottom, and we have this range of ages, continuous from 20 to 80, and then from 90 to 100. Whereas the bar graph has each discrete value, so each discrete value being a color, and there is space between them. Histograms with one main peak. So you can see here, this is, remember, a continuum of data. And when there's one main peak, that's called unimodal. Histograms with 2 prominent peaks are bimodal. A histogram where each bar height is approximately the same, so there's no prominent peak, like here, is considered uniform. Box and whisker plot. A box and whisker plot is a data display that organizes data into 4 groups. Each group represents 25% of the data, known as a quartile. Quartiles are formed by calculating the median, lower quartile, upper quartile, and the extremes. You can see them labeled here. The least data value is the lower extreme here, while the greatest data value is the upper extreme here. The lower quartile, right here, is the median of the lower half of the data set. The upper quartile, right here, is the median of the upper half of a data set. For a data set with an odd number of data points, exclude the median when determining the lower and upper quartiles. So if this is your median, but it's an odd number of data set points in the set, just ignore this one and just take the point from here up and determine the median, that's your upper quartile, or from here down, determine your median, that's your lower quartile. The interquartile range, IQR, is a positive number that equals the difference between the upper quartile and the lower quartile. All right, let's look a little closer at the box and whisker plot. The entire box, so here's the box, represents 50% of the data. 25% of the data lie in the box on each side of the median. Each whisker represents 25% of the data. Graphing. When constructing graphs, always make sure the following criteria are met. The axes are labeled with units. All given data points are plotted. The scales are consistent on each axis. The spacing must be the same along the entire axis. The spacing need not be the same on both axes, it just must be the same on each axis. If given a data table, the first column is usually the x-axis or independent variable, and the second column is usually the y-axis or dependent variable. Many different aspects of life fit this type of distribution. Imagine graphs for the height for humans, weight of bears, or size of homes. Most data would be around the same number, the mean. Yet there would be some that would be larger or smaller. Finally, you would have the extremes that would be rare. This is called a normal distribution and looks something like this. Normal distributions are also called parametric because they're completely defined by two parameters, the mean and the standard deviation. The histogram of normally distributed data is unimodal, with the mean, median, and mode sharing the same central value. A box and whisker graph of this data is symmetrical, with the median falling exactly midway between the upper and lower quartile and between the lower and upper extremes. Much of the variance of data found in experimental results is parametric. This shows the number of distribution of data in a set of parametric data as a function of the distance of each value from the mean. So here's the mean. The horizontal axis is measured in integral numbers of standard deviations from the mean. So 1 standard deviation, 2 standard deviation, 3 standard deviations in one direction, 1, 2, and 3 standard deviations in the other direction. Standard deviation will be explained in coming slides. In normal distributions, the area under that curve, we saw the curve on the previous slide, and we saw it defined by those borders on either side. So the area enclosed there is used to calculate percentages or probabilities. These percentages are the same for all normal distributions. About 68% of all data falls within 1 standard deviation of the mean. 95% of all data falls within 2 standard deviations of the mean. And nearly all, 99.7% of the data falls within 3 standard deviations of the mean. Indicated below are the percentage of data which fall within each portion of the parametric curve, with the figures rounded. So within 1 standard deviation of the mean in either direction is 34% or 68% total. Within a second standard deviation of the mean, this area is about 14% of the data. So if I added these, this is 48 and 48, which is 96% of the data falling within 2 standard deviations of the mean. And then finally, this area here would encapsulate 2% of the data. And so would this 2% of the data. And so 100%, again, remember the figures are rounded here, of the data would fall within 3 standard deviations of the mean. The magnitude of the standard deviation indicates the spread of data from the mean. The larger the standard deviation, the more spread out the curve will be. For these 3 curves, the mean is the same, 10. But the standard deviation is 1 for curve A, 2 for curve B, and 3 for curve C. So you can see how that spreads out the data. Standard deviation is calculated using the following formula, which is provided on the AP Biology reference sheet. S, which is the sample standard deviation, is equal to the square root of the sum of each value minus the sample's mean squared. So we find that value, then we add up the sums for every single value and divide by the number of values in the sample minus 1. To find or calculate the standard deviation, first find the mean. Add up all the data points and divide by the total number of data points. Then find each data point's deviation from the mean. So subtract the mean from the data point. Square each deviation from the mean. So whatever you find in step 2, square it. Then find the sum of those squares. total up all the results from step 3. Calculate the variance, so divide that sum by n minus 1, and then find the square root. Experimental data is often parametric. The accuracy of the measurement is higher if the standard deviation is lower, since there's less variance between the measurements. They're all closer to the mean. Calculating the standard deviation of a data set provides a key measure of how accurate the data set determines the mean. When comparing the means of two data sets, a key element is whether differences are due to the distribution of the data within each data set or are due to a real difference in the means of the two data sets. The standard error of the mean is critical in determining whether measured differences are statistically significant or are due to random variance in the measured data. It is calculated from the sample standard deviation, S, which we talked about in the previous few slides, and the sample size N, using this formula, which is provided on the AP Biology reference sheet. So SE mean, the standard error of the mean, is equal to the standard deviation divided by the square root of the number of values in the sample. The standard error is always lower than the standard deviation, assuming more than one measurement is made, and is inversely proportional to the square root of the number of measurements made. Increasing the number of measurements will reduce the standard error. For instance, making 4 times as many measurements will halve the standard error. Recall for parametric data that 68% of the data falls within one standard deviation of the mean and 95% within 2 standard deviations of the mean. Those same figures hold for standard error, whereby 68% of the data falls within one standard error and 95% within 2 standard errors. Increasing the sample size N decreases the standard error and more precisely locates the mean. This is seen graphically in error bars. Error bars are drawn one standard error above and one standard error below the value of the mean, if knowing that there is a 68% probability of the actual value of the mean being within that range is sufficient. Error bars are drawn 2 standard errors above and below the value of the mean, if knowing that there's a 95% probability of the actual value of the mean being within that range is sufficient. Each bar in the graph represents the set of values measured for the dependent variable in response to a different value of the independent variable. The values of the dependent variable have a mean represented by the blue bar and a standard error of the mean, SE bar. The top of each of these blue bars is the mean value of the dependent variable for a given value of the independent variable. The height of this orange bar is 4 standard errors from the mean. It extends 2 standard errors above the mean and 2 standard errors below the mean. If the error bars overlap for each value of the independent value, then there's no statistically significant effect due to the change in the independent value. You can see due to the overlap that we have between these standard error bars that is the case with these data. In this case, there's not a statistically significant difference between the first 3 bars. But there is a statistically significant difference between the first 3, or the first, and the last bar, since their error bars do not overlap. There's a 95% probability that the values for the first and last bars are different.